Hello, Rajkumar sir.
Yes, sir, I'm here.
Sir, you can start the session, sir.
Sure, sir, we can start. Right. So let me just share my screen. Let me just show the let's send now entire screen. Fine. So I hope my screen is visible. Okay, so I'll just see the chat window. If you have any questions, please put them in the chat, or you can unmute and you can ask. Okay, I'll just clarify them then and there I can. Okay, without interrupting the session much. Okay, so yeah. So there are some little bit more of analysis which we are able to look at. Okay, one such tools Multisim allows you to do is operating point. Okay, operating point analysis. Basically, it allows you to tell under what bias point your transistor will work. Okay, so active element will work. So this will this operating point will help you understand all these terms, right? So not really only transistor. Okay, the whole of the the amplifier. Okay, basically operating point will be mostly used in amplifier or oscilloscope. I mean, not oscilloscope, it's oscillator. Okay, so if the bias point is not, no, we also call it as bias point. Okay, so unless that voltage is maintained there, okay, so your amplifier may not do the job good. Okay, but how to know which is going to be the proper the point by operating point? Okay, so Multisim offers a tool called as operating point. Basically, what it happens is um, it shorts all the capacitors. Okay, it opens all the inductors. Those kind of things it does. Okay, it basically forms the equation. Okay, operating point can be easily calculated by using pen and paper. Okay, but if you ask the for very complex circuits, okay, maybe humans may not be able to do it at the easier rate. So no, Multisim offers one solution where it's going to computerize it. Okay, it's going to do it for us. Okay, basically. So let us try to implement such this new circuit. So basically, this is a C amplifier, okay, for which we need to find the bias point. So basically, we need this circuit. Okay, we need a 15 volts power supply. So next is resistors. So we need two more resistors. 4.7 kilo ohm resistor. So basically, assuming the theory behind this will be already covered in the classes, okay, theoretical classes. Okay, so for practical confirmation, okay, you can basically make use of tools like this. 2.2 kilo ohm. So I need a transistor. Before that, I'll just place these capacitors. Where do I find these capacitors? Okay, capacitors will be here. So I need a 100 microfarad capacitor. And 0.33 microfarad capacitor. DC 107. Okay, transistors will be found at transistor region. Okay, basically, you can see that 7,500 plus 7,000 plus transistor components are available. Yes. So then we complete the circuit, okay, by taking the output from here, and apparently we take a load. I don't really like to hit click and go again to place component, but rather I'll just copy this transistor and paste it here. But here you can see value is 2.2 kilo ohm, but the load is actually 47 kilo ohm. So what can I do to change the value of an existing transistor? Okay, I can just double click on this transistor, resistor, and I can just go here to see the properties. So I can change the property of that is values of property. So I can just change it here. I can change the property of any resistor like that. Okay, I can just double click and I can go here and change it. And basically I need a source. So very minimal, okay, 0.01 RMS. I give it directly. So basically I need to give it through a capacitor. Like if you see the symbol of the capacitor, it's like ceramic capacitor. Okay, but sometimes people will be wondering, how can I take is there any availability of electrolytic capacitor? Yes, sure, it does. Okay, if you see there is a capacitor and there's also electrolytic capacitor. So simulation wise, people might think what is going to be the difference. Okay, but ceramic capacitors might have a series resistance. Okay, ESR, those kind of components will come into picture. So you can modify it. Okay, I need like 4.7 microfarad. Okay, I guess the circuit is done. So you can basically, use an oscilloscope. Okay, now if you see my program is not capable of running, that's because apparently some other program is running. Okay, maybe I need to check it out. Yeah. So it's not like a disadvantage, but unlike Labview, where you can run multiple programs, okay, in multisim you can only run one simulation at a time. Okay, so that is there. So when I run this simulation, you can see this is the output. Okay, to compare the input, you basically have to give the input as well. The input basically comes here with respect to ground. So this is the scale. This is 20 millivolt scale and this is 5-volt scale. Okay, probably you can change the color. So yeah, and I'm running it at 60 hertz. That's why it may have some small. So let's try giving 1 kilohertz. Ideally, your C amplifier should have one 180-degree phase shift. Okay, but that happens only in a high, frequency. Okay, yeah, it happens. So yeah, but now our objective is to do a DC analysis, okay, operating point analysis. Okay, for that you can just go to DC operating point. You have to set at which point you want to analyze the operating point. Okay, that basically happens here. Okay, so I need to find that this place. Okay, so the properties, and I have to say out. I need to find the DC operating point at the output. I go to interactive, DC operating point, and I'll select this point called V out. And I'll run it. And it's going to show me such value. Okay, if you want to find the operating point at the output, absolute output, you can choose this as well. Right? So yes. So basically it comes near the before the capacitor only. Here only it comes. So the operating point here is going to be plus 455.310. So hope if anyone has any questions, please let me know. So like that, plenty of tools are available. Okay, operating point analysis is one tool, and just like how we saw for DC sweep, we also have kind of like AC sweep. Okay, instead of analyzing amplitude, this will sweep in terms of voltage. Okay, so not voltage, sorry. So instead of amplitude, it will sweep in terms of frequency. Okay, so different frequencies. Okay, it will sweep and it will try to check how it is going, how the circuit is going to respond for different frequencies. Okay, it will plot a graph, no, in decibels. Okay, so here we can try out. No, I'll try to show you one circuit. Okay, and other two circuits I can show you as a demo. Okay, we can try doing one circuit actually. Okay, so I just open new, no, I'll close this, as well. I'll open new multisim program. And here I will select a high pass filter with a simple circuit. I basically need a AC source. Okay, an example here is we have the experiment of high pass filter is basically AC sweep only. So in order to make it simpler, okay, you just have to give some configuration data, and the multisim is going to perform that experiment for you. Okay, maybe high pass filter is a very simple circuit, but I'll show you some other circuits, okay, where high pass filter makes, DC sweep makes sense. So AC power I have taken, and I need a resistor, I believe. What value of resistor, I don't know. 1 microfarad resistor and 1 kilo ohm resistor and 1 microfarad capacitor. So basic resistor, 1 kilo ohm you can place. Capacitor, it could be electrolytic capacitor also. You can see that whenever I try to place a component, okay, there's also a component type available. Okay, this resistor, you have different types of resistors available. Okay, like for example, carbon composition, carbon fill-in, get thin fill-in. Based on that, it's going to offer you a package. That's it. So if you go for ceramic, it's going to offer you a package. If you go for carbon, it's going to offer you a package. Okay, so based on that, it's going to offer you a stuff. So yeah, capacitor. If you go, okay, it's going to have the type of different types of capacitor. Now I'm just going to go for 1 microfarad capacitor and place it. Okay, I don't need anything like this. Okay. So people might ask, sir, why are we giving 120 volts VRMS and 60 hertz for this small circuit? Okay, so no, not really. This is just it's good. Just give me a voltage name of V1. Okay, I just need V1. My multisim is going to allot whatever voltage it has to allot. Okay, if I go to simulation and if I select, um, DC, AC sweep, is just going to offer. It's not even going to ask me what voltage parameters are going to be there. Okay, which voltage values to a strike change. No, it's not going to ask anything. Okay, but one thing which I need to ask is, okay, I need to select which is going to be the port for output. So this is going to be the port for output. From here only we'll take the output. So I need to allocate a name for it. I don't really need to allocate a name for it, but it's pretty hard to find. Okay, the net name is 2. How can we find which is 2, right? So if you go there and output, so not this one, okay, DC sweep, not the AC sweep. If you see output here, okay, there's something called V2. Okay, this is the output. That is the the place where you get the output. But no one can understand what is 2 there. So it's better if you give the output name. That's why we can go to the properties by double clicking on that wire, and we can name the it like that. Okay, currently it's named as 2. If you want to change it, you can change it as out. And now the current name is out. If you want to change it, okay, you can change it. Now if you go there, go to AC sweep. Here you can set what is the frequency range. Okay, basically for this, okay, if you calculate, it's going to show something like 167 or 160. I'm not sure. Okay, that is going to be the cutoff frequency. Okay, so it possibly give like 10 megahertz. Until 10 megahertz you can scan, or until like 200 kilohertz. Okay. And whether it's a linear scale or octave scale or decade. Okay, decade is possibly a good option. Okay, or octave or linear. Okay, how many points do you want? Okay, 10 points per decade means for every decade you'll have 10 values. Okay, or whether you need the vertical scale as logarithmic, which is mostly preferred. There's also decibel. There's also linear. Output is going to be a V out. There are also other options like how many points you have to take, maximum number of points. Okay, custom settings like appstall, windstall. These are all simulation settings. Okay, so I'll just use multisim defaults for now, and this is going to just give me a summary. I'll just try running this program, and there you go. Okay, it's going to show you the the cutoff frequency. Okay, taper down somewhere around in hundreds frequency. Okay, until that it's okay. Okay, sorry, it's a low pass. Okay, I was wondering. Oh, I made it as low pass. Okay, so obviously capacitor should be here and resistor should be here. Okay, I made it reverse. Okay, not a problem. I can. I was wondering why there was a high pass and. So again, you can connect the AC sweep. These radio rings can be okay. And again, it can be V out only. Now on the other hand, if you see at lower frequencies, the magnitude is not so much. Okay, but after it reaches beyond some certain frequency, it is constant. Okay, that's because your RC filter is making the job. Right, you can rename this as double it, and you can say like high pass filter. I'll name it as Bode plot. It is basically Bode plot. And in the Bode plot, normally we will be doing, I think, in decibels. So somewhere we need in terms of -3 decibels. So you can actually use certain tools like some cursors. Okay, you can set cursors, show cursors. Okay, again you can move this cursor here, try to find out where this -3 decibel comes. This is the -3 decibel. Okay, y-axis value. Okay, so -3 decibel value. Okay, the corresponding frequency. Okay, so this is y-axis value. Okay, this -3 decibels value and the corresponding x value, that is frequency. Okay, is what it makes as cutoff frequency. Okay, so 158 point something. Okay, so 3 decibel value is what we signify it as cutoff frequency. So these things students can visualize. Okay, so an example what I can show here for other than this is, okay, you can do AC sweep analysis for possibly other type of amplifier. Okay, that is okay, you can do that for amplifier as well. So same amplifier circuit. Okay, you can do an AC sweep. Okay, you can set the frequency range, then run it, and this is the frequency response of a CE amplifier. Okay, so here it will have it will have a band, it will act like a band pass filter. Okay, only this is the operating range of the amplifier. Okay, so below that it will not be effective, and here this after some frequency will not be effective. So this is basically an audio frequency kind of amplifier, so it's going to operate only in certain range. Okay, after which it is going to become null and void. Okay, and for electrical, okay, you can say RLC circuit. Okay, RLC circuit also can be subjected to an AC sweep. Okay, you can know what is the resonance frequency. Okay, if you do an AC sweep there, you're going to see where you're getting this peak. Okay, basically you need to look at where one comes up. Okay, so you can enable the cursor, move the cursor and come over here. So this is the value of so okay, you can say like this is equal to 1. Okay, this is the peak frequency value. Okay, and we can say like this is the resonant frequency. So resonance frequency is the frequency at which your phase difference will be 0, and your amplitude gain also will be maximum. So these things can be visualized. So any questions, you're welcome. And one more very important tool is called Transient Analysis tool. Okay, where it's going to show you, what is the starting, behavior of a circuit. So mostly people will only worry about operating, characteristics of a tool. But sometimes you need to analyze what happens when it is going to start, whether it's going to have a lot of transient or whether it's going to have a lot of spikes. Okay, those things must be carefully analyzed, because let's say we have built a faulty circuit, and every time it starts, it's going to have a lot of energy drawn up, and many times we switch off and switch on. Okay, there is a very large chance that that circuit is going to fail. Okay, pretty soon. Okay, so instead we can try to analyze how the circuit behaves during the operation, during the starting, during the ending. Okay, and we can try to create a prevention. Okay, if it is um, behaving not so good, okay, probably we need to go for some other measures to prevent it from behaving bad. Okay, we may need to add additional circuitry to make it act good. So like this, we need to modify our circuit such that the final product should be fault free. Okay, maybe your circuit may not be 100% proper, but we need to make it as good as possible. So multiple iterations of circuit design should be done. Simulation should be done. Okay, when people are satisfied with it, people should move forward. Okay, so trans analysis is one tool. So let us try it out. So for this trans analysis, I'm just going to give step voltages. Okay, basically I need to understand how it's going to act. Okay, during the switch on of a circuit. I'll go to power sources. I'll go to signal voltage sources, and I believe it's pulse voltage. Yeah, solely pulse voltage. So I'm doubling on it. It's going to ask me whether I need initial value. Okay, and I don't need initial value. I'll just give it as 0. And next is going to ask us what is the pulse value. Next is going to ask me what is the um, pulse width. Okay, I'm just going to give it 5 milliseconds. Total period is 10 milliseconds. So 40 ohm. Milli-Henry. 1 microfarad. And to identify it, okay, I'm just going to take it out of this portion. Here also I can take. I can take it in multiple places. So I named it. Now I basically need it for transient analysis. Then I need to say what is the end time. Okay, basically it's going to take only for a finite number of time. Okay, I'll just take it for like 0.01 seconds, because it's going to run this whole cycle is only for 10 milliseconds. So I'll start running it. Oh, output. Okay, output should be defined. I'll give like VC and VL. So this is how your circuit will act. The transient. Okay, as we call it as transient, it's not going to settle immediately. Okay, if you say it's going to have some sort of transient here. Okay, during the rise also it's going to have transient, and then the fall also is going to have transient. The same happens across the capacitor also. It doesn't settle immediately. Take some time. These things can be observed. So these are one of the tools, okay, which are available. Some of the tools are available in multisim. Okay, apart from the laboratory, emulation, interactive simulation, which is commonly used, okay, because of its simplicity, because it can, visualize, and it can, give a feel of laboratory. Okay, interactive simulation is commonly used, but if you want to go for specialized tools, yes, you have an operating point, you have AC sweep, you have transient, DC sweep. Okay, apart from that, you have multiple much more is also available. Okay, depending on your usage, you can go for that. There's also something like user defined, where you can write, if you know what is the type of, analysis to do. Okay, you can write a code for it, and you can execute it. Okay, I believe this help window will give you options as to how to code it. Okay, and spice comments is not really easy to write. Okay, they require much expertise. Okay, experts write it. But if you know how to write it, you can go ahead. Okay, close this. So if you have any questions, please let me know. Or else we'll see about a little bit about digital electronic circuits. Then we'll see how we can integrate Labview and multisim together. So yeah, now let's come to digital electronics lab. So there's no difference between commonly the theme is going to be electronics. Okay, it doesn't matter whether it's analog electronics, whether it's a digital electronics, whether it's a mixed signal, mixed signal electronics. Okay, multisim is capable of it all. Okay, if you want to go for power electronics, okay, I'm not sure if people are here from Tripoli. Okay, you can also simulate power electronic circuits also. Okay, your multisim is very, very, very well capable of that. Okay, so we have electronic components, okay, digital electronic components. Okay, where do you find them? You have many places to do use it. Okay, you have TTL, okay, where we emulate the actual IC model. Okay, you have something like 74 LSIC, those things you have. You also have something like CMOS based circuits. Okay, I'm not sure how many colleges use CMOS based circuits. Okay, most of the time I have observed that most of the people will use TTL based. Okay, 74 series is very famous. But if your college uses CMOS based, go ahead. Okay, you have those as well. Or if you don't want to work with a specific component, okay, you want to go ahead with a very generic. Okay, you have something called this digital. Okay, where you can use generic components. Okay, in this digital, okay, you have generic components without IC number. Okay, you have and 2 and 3 and 4 and 7 like this. But if you want to implement this in real world, let's say you want to build a PCB, then you probably have to use either TTL or CMOS. Okay, probably sound for LSIC where you're going to have this package. So once you export it to a PCB design software of LAVNI, okay, they are going to be able to create that circuit. So everything happens for everything is for a reason here. But let's say your objective is not for PCB design. Your ultimate goal is not for a PCB design, and I don't know you if you are not sure what is the number. I mean, most of the faculties or teachers will be aware of the component name. Okay, but you cannot say the same for students. Okay, to make it simple for them, you can use mixed digital components, and there you go. You have like and 2 and 3, so they can use this. So ultimate goal here is to make them do the experiment. Okay, so see if let's say I want to do an AND gate, I can use an AND gate. I got an AND gate. Okay, now I want to give it the input. So in our laboratory, for an AND gate, we will give an input from a 5-volt power supply and 2 switches. Okay. So now we need to get a switch, and to look at the output, we probably need an LED. Okay, so Trayer kits will be available actually in colleges, most of the colleges. Okay, or some people will be using Elvis. Okay, but this is a circuit simulation environment. So let's go for basic switch. Here something called dip switch. See, switches is available. Then I have 5-volt power supply. Then the ground. Okay, I don't need a 12-volt power supply for this. I can probably use a 5-volt power supply for this because it's a TTL. And for LED, I have this diode. LED, I can use any color LED I want. Okay, there's also IRLD, but it doesn't really make any sense. So only when both of them are true, okay, you're able to get the output. But let's say you want to emulate the actual components. There are two methods to do that. The TTL, if you see, your ultimate goal is to make students understand how to build the circuit. Okay, that is also one of the ultimate goals. Okay, apart from making them understand, for making them understand, you can use this mixed digital. But in reality, if you go to a lab and if you see, there'll be ICs. Okay, so in that case, a contradiction is happening. Okay, so in that case, obviously, you have to use this ICs. And there are two options. Either you can use this ICs in this simple format, or there's the option of ICs itself. Okay, in this case, okay, it will be as the IC is available. Okay, you have VCC. The format of the IC will be preserved. Okay, that is this DO14, the package, 14-bit package. Right. So those are the one of the options. Okay, let's try some other circuit. Okay, not only simple circuits like this is available. Okay, you can also build something like complex circuits as well. Okay, so but before that, you really need not use only LEDs. Okay, possibly you can also make use of some tools which are available in Labview. Okay, called as this logic analyzer. Okay, you can use logic analyzer also um, to analyze how the the circuits will work. Okay, so for that instead, I can remove this circuits. The values these are emulated by the user. Okay, that's why it's working like this. Okay, but let's say I want to give automated input and automated output. I have to possibly make use of some sort of clock pulses. Okay, not to make it more dynamic. So make use of sources, single voltage source. I'll make use of clock voltage source. I give something like 100 hertz, okay, 25 volts. Okay, it should be something like 00011011. So if for A, if I'm giving 100 hertz, okay, so possibly for B, I need to give 200 hertz. It needs to be fast. Okay, 0011. 0011 is 100 hertz. Okay, 0101 should be twice faster than that. Okay, so I can just copy this and paste it here, and I can make it as 200 hertz. And output. And also we need to give some external clock for it, because logic analyzer needs some external clock. Let it be one, like 2 kilohertz or something, 10 times more than maximum. So for logic analyzer, we need the inputs. Oh, okay. That's strange. Okay, sometimes in your program, okay, you'll be having something called stimulation error as occur. It is because your program is basically ordinary differential equations. So if such errors occurs, okay, you can possibly try to run the convergence assistant. So it'll try to analyze the situation. It will try to check where the error lies in. Okay, and the other circuits related to this, they are given it from function network. So instead of this clock pulse generator, okay, I'll probably make use of this function generator which is available here. I'll have 2.5, 2.5. I'll keep this as like 100 hertz. It is quite good. Okay, one more. Okay, I shorted it to ground, output to ground. Okay, maybe that's why. Oh my god, okay. So that's the reason. Okay, why it happened. So silly mistakes like this will happen. Okay, probably you could have used that clock only. Okay, kilohertz clock. So you keep on running. So you can give like 5 divisions per clock. Only when both of them are true, we are going to have it as true here on the third. These things can be very well analyzed by using your tool. Apart from that, you can build a very complex circuits. Okay, no matter how complex your multisystem should be able to handle it. Okay, you can build like encoder, decoder, multiplexer, 8 cross 1, 4 cross 1. Also mixed the signal values like ADC, DAC also you can build. Okay, so one such example is open here. So ADC is available here. So you can vary this value. So you can see for every 1 analog voltage generated, it's going to show us some digital value. So it's 8-bit no ADC. So that's about it. You can also build something like a complex circuit like this is SISO. Okay, data will give it. Okay, and data will go from one in. Okay, it will keep on going. A single input, single output. Like this also you can build. Yeah, also have flip flop as a component. Okay, let's try building this. Then we'll go for um, how we can connect Labview and multisim together. That's very simple. So we'll build one last circuit and we'll proceed. So one function generator is going to be for data. Okay, flip flop I believe can be found at Mist Digital. KJK flip flop. It's here. Not get also will be somewhere here. You might be wondering why I gave 2.5, 2.5. Okay, basically this is V peak, meaning it will generate voltage from plus 2.5 to minus 2.5. I don't want plus 2.5 to minus 2.5, I want 5 point volts to 0 volts. Okay, so instead of that, I cannot, if I give 5 volts, so it will generate minus 5 to plus 5 volts. But if I want 5 volts to 0 volts, okay, I need to give 2.5 and 2.5. Basically, this 2.5 is offset, it will add 2.5 to this. Basically, the positive 2.5 will become 5 and minus 2.5 will become 0. So that's why I'm doing something like this. And JK flip flop, I need 3. Copy and paste this. Oh, okay. It should be interactive. Okay, we are certain only output. Okay, but SISO's objective is no, the data passes between one end to another end. So you have to observe that. Basically, need to, this is the input. This is one step after, and this is the other step after, and ultimately at the end, it will become something like this. And I will color here also plays a factor of, you know, the plotting. I think. There should be a way to look at zero from zero. Yes, yes. Here you can see. Okay, first color is my input. For input and this one there is no much difference. But after next clock only your the next value goes here. Okay, and this value reaches here only after the third clock. So 1, 2, 3. Third clock only this reaches here. But during the first clock itself, this value is instant. Okay, it goes over here. But in order to realize this value here, okay, it needs to be this next second clock. It is first clock, second clock, third clock. So the more clocks per division if you give, the more number of times it's going to run. It's going to take time to run. It hasn't returned value yet. So yeah, so you can build some circuits like this, and you can ask the students to visualize it. Okay, I hope this was useful. Okay, so the ultimate gain here is Labview is not only used for analog circuits but also for digital circuits. Okay, you can simulate as much as you want, whatever components is required in Labview itself. Right? So Next, let's see about how we can integrate Labview and um, multisim together. Okay, basically that's one a very useful tool. So let me just close this everything quickly. Yeah. So why do we need to go for Labview multisim co-simulation? Okay, that question might pop up. Okay, so basically there's a reason for it. So mostly Labview will be the tool, okay, which is going to be interacting with several other hardwares. Okay, let's say in future you want to integrate one of the circuits you're going to work with with hardware. For example, let's say you're going to build an oscillator, you are going to build an amplifier, okay, and that amplifier needs an input. Okay, that input is going to be some of the hardwares of NI or some other third-party hardware which is going to generate that signal. Okay, then you want to give it to that amplifier, and then you have to visualize the output. Okay, in this case, first we need to test that whether that circuit is working properly or not. Okay, since we're using Labview to control that hardware, and we have a circuit in hand, instead of building the circuit, instead of going to the shop hurriedly and buying the components and trying to build it, first simulate that hardware. Okay, check whether every parameter of it is perfect. Okay, whether any power components are exceeding. Okay, or not. Okay, you can check it. Then ultimately, you can um, after testing it stringently, okay, you can basically pass the same signal whatever you generated with Labview to that hardware. So that's why first control that circuit using Labview. Once you're satisfied with it, next you can control the same algorithm, whatever algorithm you develop, you can pass it to this hardware. Okay, so this applies. Let's say if in electronics, okay, you can talk about oscilloscopes. I mean, oscillator. Or if you're talking about RF, okay, you can talk about RF circuits. Or if you're let's say if you're an electrical engineer, okay, power electronics engineer. So basically, you're going to control, boost converter, buck converter, inverter by using some sort of logic. Okay, how the gate should be switched on and switched off. Okay, so in that case, you can build the circuit model of the multisim in the circuit model of the converters in the multisim, and send the signals whatever you will send it normally inside it. Then once you're satisfied with the response, okay, you can send the same signal from Labview, same signal, whatever signal you send it from multisim, the same signal you can send it to hardware, and through this hardware you'll connect the circuit and realize the whatever is happening. Okay, for this we'll try to implement a full wave rectifier and pass the data to Labview. Okay, so let's see how we can build it. So by default, when I say full wave rectifier, you can have only fixed voltage when you're working with multisim. Okay, fixed voltage and fixed frequency. But when it comes to Labview, you really don't have to worry about that. Okay, you can set any frequency you want. Okay, now let's go to Labview. Anyway, you will be exposed to Labview more, okay, in the coming days. But let me just give you a brief introduction of what Labview is. Okay, Labview is basically a laboratory, tool. Okay, it's a system design tool which is used for programming, and it's not like normal programming tool. Okay, it's full graphical, right? Um, when you see upcoming sessions, mostly everything will be on Labview, right? So let's see how we are going to use Labview. So first I'll start building the circuit. So I really don't need to do the same circuit. Okay, I don't need the transformer and all. It makes the things much more complex. So what instead I will do is I'll make use of the FWB, the full wave bridge rectifier. Okay, it's available as a component. Okay, so we are going to make things much more simple. Okay, if I give you the input in one pair, there are two pairs. Okay, the output is going to be different in other two pairs. So here I will be probably needing an AC input. First, I will be filling the ground. And now AC input. Okay, I really don't have to give it from multisim. Labview has its own AC input which I can give. A signal generator I can use. But how do I integrate both of them together? Okay, for that I have a tool called as multisim Labview co-simulation connectors. Okay, which I go to place, connector pin, and Labview co-simulation terminals. Okay, I can give it as voltage input. Okay, I can rename it as sine input. And output will be basically viewed upon the other two pairs. Oh, sorry, it should be opposite pairs. If you sine wave through this point, okay, here the AC will come. So here across, I can take the output that is going to be DC. I'll take it across a load. So I'm going to make the measurement right. So measurements. I have to make across. So there is the output connector. Okay, Labview co-simulation output connector. Okay, voltage output terminal. Okay, since I will make it across. Okay, this if I place one. Okay, this measurement will be with respect to ground. Now I don't need no with respect to ground input output, okay, because it's DC and it's isolated. Okay, so what I'll do is I will place two. Okay, since Labview is a programming IDE, I will subtract it there. So it's as simple as that. Okay, once you define it, okay, in Labview you can just plug and drag and drop this inside, and you can use it. This is the Labview window. Start programming. Okay, I'll just go to UVI. And before I import this model is created, I have to save it. Okay, possibly in desktop as no FWR. Yeah, close this, and there will be a lot of programming options will be there for Labview. Okay, but what we are going to do is we are going to do for simulation. Okay, basically multi-simulation simulation. So in that, if you go to external models, you will have multi-sim, simulation model. But before simulating, we need to create something called simulation loop. Basically, it is used to do a software and loop simulation. And inside this, I need to go to simulation, models, multi-sim design. I browse for the multi-sim model, desktop. Okay, so here I have this, in the simulation, I have this, sources available, signal generation sources, out of which I just take a sine signal. So I can basically give a sine wave of 230 volts or whatever it is. Okay, I'll go for 12 volts. We'll set it plus 12 to minus 12 volts. Frequency, I'll probably go for 50 hertz. I'll leave it as input. Output, basically I need to subtract both of them because I need to make a differential measurement. For subtraction, I have a program, Labview. Everything here will be graphical. So basically I need to subtract output and input. Both this output, both output. And plotting is also very easy in both control and design. Yeah, something called graph utilities, sim time waveform. And for simulation also, we have a lot of options. Okay, whether you want to simulate only for finite number of times or infinite number of times. Apart from that, I already told you that multi-sim models are ODE. Okay, there is a ODE solver also available. If you want more accuracy, you want to go for more variables. If you want less accuracy or more speed, okay, you want to go for lesser variables. So trade-off will be there. Let's try running. We need a ground here. Okay, probably I made some mistake. Okay, but the thing here is, okay, this is how we can bring, Labview inside, okay, in this format. Okay, okay, I've added it. Maybe I have to replace subtract. Yeah, okay. The thing is, this is how we can communicate between Labview and multisim. Okay, you can give the signal inside Labview and you can bring it back into your multisim environment. Okay, so if you have any questions, please let me know, or else we can conclude this session.
Okay, thank you, Rajkumar sir, for your wonderful explanation on circuit simulation and its analysis. Thank you, sir.
Yes, sir. Thank you very much for giving me this opportunity. It's an honor, and I would like to conclude by saying multisim is a very wonderful tool for circuit design and design platform. It's not only limited to circuit simulations; it can also go for system level design as well. Okay, so with that, I would like to conclude the session. Thank you very much.
Thank you, sir. Thank you, sir.